Okay, we're going to talk about the steady state of the Markov matrix. Okay, so before doing this assignment, it's important that you have um, done the revision village assignment uh, from earlier. And the assignment that I'm referring to is 9G.1. And in 9G.1, they talk about long-term steady state. So if you did this beforehand, this is a really nice summary of what it is we're about to do. So they kind of just wanted you to experiment with these uh, matrices that they've listed here and to see what happens when you multiply the matrices to a particular power and as the power gets bigger. So I'm just going to type in this first matrix here right now. It's 3 by 3, 0.2, 0, 7, 9. Hopefully I've typed them all in correctly. Okay, second mode to quit, second matrix, enter. So we're going to do this squared and see. I just wrote them down. I don't expect you to write all these down. That would just be crazy. So what happens if I put this to the third power? What happens? Okay, it's similar, but what happens if I do it um, to the fourth power? Then I get these values. Okay, what happens if I do it to the 20th power? Then I get, they're kind of close to this. Now, notice, so this is if I do it to the 50th power that I've written down here in red. And notice these values are getting closer and closer to this value here. So if I'm going to be crazy here. So what if I do this to the 100th power? Notice how they're going to be the same. So what is happening as the powers of the transition matrix get bigger and bigger and bigger, they start to converge, and the matrix starts to be the same. Okay, and a lot of this idea with steady state and transition matrix was kind of worked out and figured out by this guy Andrei Markov. So now, with this matrix here, this is a very interesting and special matrix. This won't be on any sort of IB test, but it was just interesting to see. Whenever I typed this into an even power, we got the same answers. But when I have it to an odd power, the zeros and the 0.5s and the 1s alternated. So that was just useful. That's called an alternating one. And then similar results with D and with E. So, so the important thing, you might want to hit pause if you want to copy any of this down. The important thing is that the patterns converge for B, D, and E. So for these three transition matrices, as the power gets higher and higher, then the transition matrix turns out to be the same. One thing that's useful, if you want to know how I'm getting this typed in, all I was doing was hitting second and enter, and then I'm going up here and changing it. Now, what happens if I make the power really, really big? Like, I'm going to make it 1,000 to see what happens. Bam! Go to quit. Okay, so that happens if you make the power way too big. Okay, so instead of to 1,000, I don't know what the maximum is. 500? No, that's too big. Okay, so 200. Okay, it'll still do it to 100. So, like I said, if it's to the 500 or 1,000, it's just too big of a power. So, okay, next page. So, you may want to hit pause to copy this down, or hit. I'm just going to read through what we have here. So, so for each sequence above is classified as absorbing, regular, or periodic. So absorbing state is when it's entered and cannot be transitioned to another. You won't see absorbing on a test. So what would a definition of the others be? So this is what I got from the textbook. A regular transition matrix is one for which there is no deterministic pattern in the sequence of matrices. And a periodic transition matrix is one where the sequence of matrices has a repeated pattern. Okay. The patterns for B was regular, for C periodic, D absorbing, and for E it's regular. Okay. Now for number 5, for Markov chain, the transition matrix, as we go T, as the power gets bigger, then the values on in the entries will become constant. They won't change. So, and as I said earlier, regular transition matrices is all we're going to be discussing from here on forward, and so you don't need to worry about absorbing or periodic or anything like that. And that's what they'll be testing you on the IB tests, and those are the calculations we're going to be learning how to use. Okay, so somebody asked me about this one earlier today, so I'm just going to draw it and talk about it. So if I've got so the current state and future state. Okay, so here C stands for Coca-Cola and P stands for Pepsi. Okay, so if I start off at Coca-Cola and then future still like Coca-Cola, that's 0.75. If I start off at Coca-Cola but then I start to like Pepsi, that's 0.25. If I start off with Pepsi and then switch to Coca-Cola, that's going to be 0.2. And if I start off with Pepsi and then I go staying with Pepsi, that's going to be 0.8. Okay, I hope people are good with making transition diagrams and switching back and forth from the diagrams to the matrix. Okay, so what we did with our revision village assignment is that we discussed when T is large, when N is large, then our transition matrix, if I have this power large, then we're going to find the steady state. So let's talk about this. What do we have here? So this matrix here is our transition matrix, and this value here is our initial state vector. Okay, so in this example, there was 126 customers, 81 bought Coca-Cola, and 45 bought Pepsi. Okay. Okay, this is the page that is probably important. So, so our initial value is these are the number of people that were buying Coca-Cola and Pepsi. Let's see, Coca-Cola is on top. Yeah. All right. And then after the first year, so this is initially, after the first year, it's our transition matrix times our initial value. Okay. And then after the second year, it's going to be this transition matrix times the other transition matrix. So basically, this value here, where is my red pen? Gosh. Okay. Well, don't know where it is, but this matrix right here, this is the transition matrix squared. And this one here is a transmission matrix cubed. Okay. And so on. So if I do my transition matrix to the fourth power times our initial state, we end up with these values here represent the number of people liking Coke and the number of people that like Pop C after initially. This is after 1 year, after 2 years, after 3 years, after 4 years, and then we start seeing what happens after 10 years, 20 years, 49 years. And notice they start to converge. At some point, for example, after 10 years here, at some point, you're always going to have 56 people liking Coke and 70 people liking Pop C. And this is including that some are going to switch liking one or the other, and the transition state stays the same. Okay, so as I do this to the 10th power, my transition state starts to become the same matrix. Okay, prior to that, the transition state is transitioning until we get to higher and higher powers, and then it starts to stay constant. You might want to hit pause if you need to check this. Okay, once again, you may need to hit pause. So once again, as I said earlier, as the power gets larger and larger, the transition matrix converges, which means the values just kind of stay the same. And also S sub n converges. Okay, generalize these convergences using long-term probability matrix and a steady state vector. Okay, so t to the power of n, as n gets really big, we can call x our long-term probability matrix, and we'll use that in a second. And as the consequence matrix x satisfies my transition matrix times x is going to give me the same thing. So an example of that, here is my transition matrix times this value. That doesn't look quite right, but is going to give me my long-term probability matrix. Okay. Number 4. Okay, what interpretations can you make of these patterns regarding long-term market share? So basically, our long-term interpretation is that starting off with 120 people drinking Coke and Pop C, eventually 56 will like Coke and 70 will like Pop C, and they'll just be that way forever. So what is this assuming? This is assuming that the population is always going to be 126 people. Okay, so whenever you're doing steady state calculations, the population has to stay fixed. Also, the other thing is the transition matrix has to stay the same. So they can't change the formula for Coke and make it more desirable, or change Pepsi to make it a smaller can or something like that. So the transition matrix has to stay the same in order to establish steady state. And then question 6, how can we use power of the transition matrix to make predictions? So basically, as we said earlier, as the power gets bigger and bigger, then our long-term matrices will be reached. Okay, so in example 11 here, I not only did I copy the question, but I wanted to make sure that you had the answers for this as well, so that when you did the assignment, you would have an idea of what's going on. So they've given you an initial state vector of 110, 80, and 50. Right, so that's my initial state here. Good thing I put the solutions here because the matrix didn't show up somehow. Okay, so calculate. So this is our transition matrix. Okay. This is our transition matrix, which I did not put up here in the question. So calculate the likely number of bicycles in each zone after 5 days using the transition matrix. So from example 10. So this should have been here from example 10. So if I have this matrix and put it to the 5th power, you end up with these values. Okay, and if I want to find out what it is like at a steady state, I'm going to pick a large power. Okay, let me type this in real fast so you can see what it did. Okay, clear. 3 by 3, 0.5, 0.3, 0.1, 0.3, 0.35, 0.3, 0.2, 0.35, 0.6. Okay. Second mode quit. So I'm going to do that matrix to the power of 5, and then, oh, I don't have the other matrix in here. Uh, 110, 80, 50. Okay. Okay, so times matrix B. So this first matrix is this one to the 5th power, and there's a second matrix, and so these are the values we get. So approximately 66 math bikes are in zone in the first zone, and then the next zone, and then the next. Okay. So zone C, zone I, and zone O. Okay, I guess some of that question was in example 10, and I don't have that printed here. So, okay. So if I have it to the 50th power, then these would be when it reaches equilibrium. Okay, let's move on. Okay, and so comment on how the owner of math bikes should reflect on this with the steady state and the limitations. So the model's not going to work if there's outside events like bikes being stolen, damaged, that sort of thing, for bike rental. And so you can read this. Okay, so now we've got, this is an example of a transition diagram, which we played with already. And we can write this into a transition matrix. And it says from the investigation, that's from somewhere in the textbook. Sorry, I didn't have that in here. But we're going to talk about steady state here. So if I wanted to do it by hand without doing it, just picking some large value, they show how to do that here. We probably won't be doing it by hand, but if you want to know how to do it by hand, you've got it here. Okay, so you might want to hit pause if you want to copy this down. So does the steady state probability vector depend on the initial state vector? No. The initial state vector does not matter. So and this is important. So if I go back to the POP-C question, this one here, if I had put other numbers besides 81 and 45, but the total was still 126, this S sub n value would still remain the same. So these initial values don't matter as long as the sum of them is the same. I'll do an example in just a minute. Okay. So like I said, this other way, method 2, is using some algebra, but I think the best way is to use method 1, where you just use your calculator and find a power of n that's very large. So here's a matrix. Find the long-term probability matrix for the Markov process here. So let's just do this for example. So 2 by 2 matrix, 0.13, 0.45, oops, 0.71, 0.87, 0.29. Okay, and I'm going to put that to some large power. Oops. $100. And then I get these values. Okay. 100 is a large value. That's fine. Something very, very important whenever you're doing these transition matrices is that all of these probabilities, because this is probability, right? Right, probability. Since it's probability, these have to add up to 1. The sum is 1. The sum equals 1. Okay. And they mentioned that on the previous page, I think. The sum of the matrices, the sum of the probabilities has to be equal to 1. So like here, those sums have to add up to 1, and these sums have to add up to 1. Okay, I know it talks about eigenvectors and eigenvalues up here, and we'll be talking about those in the next lesson. Okay. So same process for these. You might want to check your answers. Hit pause. Okay. Same process for here. If I enter this in and do a high power, you end up with getting this. And notice how the rows 0.32, 0.32, 0.32, 0.27, 0.27, 0.27, 0.41, 0.41, 0.41. So when you're doing a transition matrix, you're going to find that the rows are all the same. If you go back to the previous example, you'll see the same thing. The rows are all the same. That tells you that you've reached the steady state. So, and once again, I have the rows are all the same. Okay. You may want to hit pause. So I've got my transition matrix. We want to know after 2 years, so my power of this is 2. And my initial state is 45% A, 25% B, and 30% C. And once again, all of these values have to add up to 1. All 3 of these add up to 1. All 3 of these add up to 1. All 3 of those add up to 1. And so if I put this in the calculator like that, we should get this value. Calculate the long-term matrix. So once again, I do it to a large power. Here, once I did it to 100, and as I said before, the rows are all going to be the same. So we're going to assume that the transit. So our assumptions is that the transition matrix doesn't change. Hit pause if you need to copy this down. Okay, question C. Okay, so by comparing the matrices T, T squared, T to the fifth, T to the 20th, comment critically on the likelihood that the transition probability remains constant. Okay, so realistically, it's probably not going to happen. The people would notice, the companies would notice the trends that are happening, and they might change their prices. And at which, if they change their prices, that changes the transition matrix. So, so this only works if the transition matrix stays the same. So that might be one of your limitations. Okay, you may want to hit pause and check your answers. Okay, once again, you could hit pause and check your answers. Okay, you may want to hit pause and check your work. Okay. Here I solved it algebraically. So I used my transition matrix, and I said A and B and A and B, just like they did on the one. So this is an example of that. Might want to hit pause, and you may want to hit pause. Okay, I hope this helps, and I hope you have a nice weekend.